Alright, nerds, so today we're going to start with the history of the atom. So we've got our current model of the atom, and that's all good and well. So we're now going to look at how we got to where we are now. But yeah, so let's go. First there were some Greek dudes, a guy called Democritus, and I'll be honest with you, I tend to not include them because their ideas, although they were kind of correct, they were a guess. They were no more valid than the ideas that came before. Sorry, it became before and after. There were competing ideas at the same time. Democritus, he had the idea that all of the atoms were these, I guess like this down here, these tiny little balls, and other guys thought that you could just keep splitting them forever and ever and ever. But it wasn't science, it was philosophy. Both were, according to the evidence, both were equally correct. So we're not going to worry about those guys too much. But we are going to talk about what's his name, John Dalton, who was an English physicist. And he proposed, so actually the first cool thing he did was he calculated the atomic weights. Now we're talking something that's, we can't even use grams because it's so small. But he calculated that, which was really cool. But he proposed the atomic theory, which states, and it's the first real atomic theory we have, that all substances are made of atoms, and they are small particles that can neither be created, divided, or destroyed. Okay, that's important. Atoms are the same element, are exactly alike, and they are atoms of different elements are different, and he was talking about in mass how heavy they were, and they'll join together to make new substances or be rearranged. But basically, if you look at his first state, look, they're all correct. This one here is so correct. It's correct for high school, but not, you know, when you get beyond that, it's not so much. This one here, that's correct. That is incorrect. Okay, and that one's kind of incorrect. So he was pretty spot on. And basically, they were little spheres, and they look like these guys down here. Alright, so Thompson, he comes along, and he uses a cathode ray which shoots beams of light, essentially. He found that cathode rays in a Crookes tube were attracted to a positive field. This means they had a negative charge. So basically what he was doing was he had a Crookes tube, which is what you see down here, and you put an electric charge through a gas, and beam of light goes across. He worked out that they were individual particles, and because they were attracted to a positive field, they were negatively charged. So he had electrons. He discovered electrons. So basically, he's worked out that in the gas here, the atoms they're not a solid lump. There's things in there which can come off, and he called them electrons, sorry. So he showed that cathode rays were, so that this beam here is called a cathode ray, were caused by electrons flying off the atoms and colliding with stuff. Then what is also cool is he found out that they were the same regardless of the gas. Okay, there was no difference in them. Therefore, electrons exist in all atoms, and they're the same. Like, there's no difference in them at all. So he came up with what we call the Plum Pudding model. So you have a positively charged sphere, still like Dalton, but there's embedded in it these little negative electrons, and this is, you can ignore this for the moment, get rid of that. That's how he was claiming electricity works. Ignore all that. We're going to focus on this. This is what it looks like. So you have a positive sphere with little electrons thing, and that's called a plum pudding because, well, we'll talk about that later if you don't understand it now. Rutherford, he was our New Zealand farm boy who moved off to England and stopped calling himself a Kiwi. I don't know why. It's a pretty great place. But he was like, basically, look, Rutherford was a bit of a jerk. But he was allowed to be because his work was so cool that he got away with being a massive tool. And that's fine. Alright, so he fired beams of alpha particles, which you would call a helium atom minus the electrons that we just discovered. So he fired that into gold foil, really thin gold foil. Most went straight through, or they didn't go straight through, they sort of bent a little bit. So about 1 in 8,000 deflected off. And he then came up with a model of the atom called the planetary model. Okay, so this is what he looked like. Here's our observation, and here's our conclusion. So he fires the beams through, boom, 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 and most of them go straight through. What this means is that the atom is mostly empty space. Mostly empty space. Some bent. Now, what this means is, if it's mostly empty space, there's a positive part and a negative part, because we know that helium nuclei are positive. All right, class. We've now got a little guest. Sit down. Okay, so where were we? Basically, these positively charged atoms, they fly straight through, and they deflect off because like charges repel one another. Okay, but that meant there was a positive and a negative separate section to the atom. The really cool part is he fired helium nuclei, so no electrons, just the protons and neutrons, which are really light compared to gold nuclei. Some of them flew through. 1 in 8,000 hit and then bounced straight back. He described this like firing a cannonball at toilet paper and having the cannonball bounce straight.
Toilet paper.
Having the cannonball bounce straight back. So what this means is, because we know that if you bounce a ball at a wall and it bounces off, that's because the wall is much, much larger. So that meant there was a very, very dense, hard nucleus, and it was obviously about 1/8,000th of the total size, because 1 in 8,000 bounced off. But there's a very dense, heavy nucleus. The stuff bounced off. That's what Rutherford gave us, and that's essentially the beginnings of the model that we have now. And Rutherford was awesome. He was really rad. All right, so his model looks like this. So you've got the nucleus in the middle. There's a helium atom, and the 2 electrons orbiting around the outside. Alright, so make sure you draw that down. Now, Bohr. He was a Danish dude who was pretty rad, and basically he studied what happened to electrons or atoms when you heated them up. So if you excite an electron, it actually, so as you put energy to it, it absorbs light. But when it cools down, when it calms down, it releases light, and that's what we see here. Each different flame.
That's pretty.
It is pretty. Each different flame has its own color. So each different element has its own color flame. All right. So he basically studied that light was produced when atoms were excited by heat or electricity, which is cool. And Rutherford's model couldn't explain why the colors were unique to each element. Bohr's could, though. He proposed that electrons are in orbits. Basically, when they're excited, they jump up to a higher orbit, and when they're relaxed, they drop down to a higher orbit. And when they're relaxed, they release energy and give off a photon. So,
Funny.
so this is Bohr's model, and this is the model we tend to use. Now, what it says is that there's specific orbits that electrons can have. You can't have too many electrons in each orbit, because you can have one there and one there, but there's no room for another one. So in this one you can have that one there, one there, 2 there, and 2 there, but there's no room for any more, and it goes up each level. But so basically he's put forward the idea that there are specific orbits and they tend to live closer to the nucleus. Alright, so that's it. That was long. Good luck with the notes. Say bye, Audrey.
Bye.